In 2011, MIT and Belimo collaborated on some test installations at 6 air handlers in our Hayden library, and with the expectation of trying to try different strategies for delta T mitigation in the chilled water system. So of the various strategies that we were able to test, to cut to the bottom line, the one that we suspected would be the most successful and is if you actually measure delta T and control for delta T, you're going to improve delta T. So all the details to getting there and how they're able to put this in one smart actuator for local implementation and so on will come from my friends from Belimo. All right, where do we need to point this? There you go. Here you go. So just for a little background, we have a central chill water plant at MIT with about 20,000 tons of steam turbine-driven chillers and another 13,000 tons of electric chillers, both at the central plant and at a satellite plant. And also in this collage of pictures down in the lower left is the Hayden Library itself, which is about 153,000 square feet and has 6 air handlers. This extracted from a study that was done by WM Group back in 2008. And they identified, they were helping us with our chilled water delta T problem and did a study of our plant, our dispatch, our equipment, very specific to us on what was the potential savings. So, and you can see that it's significant, $1.5 million. But the interesting takeaway from this is that it's not just the chilled water pumps energy, which in fact is only about a quarter of the whole damage. The rest of it is if you have to bring on extra chillers to satisfy the flow requirements, there's the inefficiencies there, plus the energy to run the associated cooling towers and so on. So when you're looking at the impact, there's a 4x multiplier to be considered. And then another graph I took from that WM Group report just is a scatter diagram showing that there's really very little time up in the upper left-hand corner there, under 1,000 hours, when we're doing better than 8 degrees delta T. So again, a lot of potential for improvement on our campus to help the improved operation of the central plant. So at this point, I'd like to turn over to Dick to talk about our installation.
Thank you, Peter. Just to kind of reemphasize what Peter just mentioned, in fact, the chill water plant has a 12-degree delta T design, and it does operate like 2 or 3 days of the year at design condition. But the rest of the year, it's subjected to this really abysmal delta T, low delta T condition with a lot of extra energy that is expended because of that. So what is actually driving that? This is just basically refrigeration. Q is equal to MC sub P delta T. It's just energy. But what's key about this is that the delta T and the volumetric flow are inversely proportional. Therefore, if your flow increases, you're going to get lower delta T with a constant cooling load. All right? And that's what you're looking at over here. What causes low delta T? Essentially, you're overflowing the coil. And it's not just at 25% of load or 50%. You're basically continuously overflowing the coil. The main reason for that is that all control valves are oversized. Why are they oversized? Well, when an engineer specifies the cooling load for a building, he has a particular valve coefficient that he specifies for the valve. When the controls contractor buys the valve, there's no valve that has that precise valve coefficient. Does he put in a smaller valve? No, he puts in a bigger valve. So you're basically sunk from the very beginning. All control valves are oversized. Another big reason is improper balancing, non-dynamic balancing. That basically means you're not using pressure-independent valves, which address that dynamic balancing issue. You may have dirty or fouled coils, and then the list goes on and on. There's another 10 or 15 reasons for low delta T. Okay, just to, everybody here knows what's going on, why this adversely affects the chilled water plant, but just for purposes of discussion, say for example, we have a 400-ton chilled water plant with comprised of two 200-ton chillers running at about 45% load, 100-ton cooling load. Design chiller delta T is 12 degrees, so therefore you should, by virtue of that equation, you should have a 360 gallon per minute demand for pumps. This is the way the engineer designed it. In fact, when you turn on the plant, you actually have a 15% higher volumetric flow requirement. What that causes is that you've exceeded the pump capacity of one chiller. You have to turn on the second chiller because your load has, your volumetric requirement has gone to 414 GPM, and your delta T has depressed to 10.4 degrees. That's why you end up running multiple chillers at significantly less capacity. It's this low delta T volumetric flow requirement. At the going back to the load history for MIT, even at the lowest loads, they're running 3 or 4 chillers just to take care of the volumetric flow. Any one of those chillers could take the capacity if it were running at the proper delta T. Okay, so you're running additional pump and a chiller, starting to meet the flow and demand, not the cooling demand. And again, it's not just the pump. You have to run the condenser pump, you have to run the cooling tower fan, and the energy just starts getting very expensive. So here it is. You've increased the flow by 15%. The delta T is lowered by 13%. All right, so here's the Hayden Library. Again, it's 153,000 square feet, 6 air handling units ranging from 5-inch chilled water valves down to 3-inch valves. It was reported that it had a 6-degree delta T. There was overpumping, and it was causing low delta T syndrome at the chiller plant. For the purpose of this case study, we replaced all 6 of the air handlers with what we're calling the energy valve. And that involved putting 2 RTD temperature sensors, one in the return line and one in the temperature well in the supply line to the chilled water coil. And then we put an Ethernet drop so we could get data off the valve, and it was being driven or controlled by the analog input coming from a carrier DDC control system. All right, so what's an energy valve? It's comprised of these components. It's a conventional equal percentage characterized ball valve. And like I said, they ranged from 5 inches down to 3 inches for this project. In addition, it has 2 RDT temperature sensors, one that's actually sunk into the body of the valve, monitoring and measuring the return chilled water temperature. And then the second RTD is remotely installed into the supply line going to the coil. In addition, it has a magnetic flow sensor, and then it has an actuator, but it's an actuator that not only modulates the ball position depending on the signal, but the actuator also has a microprocessor. It has a data acquisition system that actually records and keeps 13 months of data. It also calculates it doesn't just measure T supply, T return, it calculates the temperature difference, so you have delta T, and then it actually does the mass flow, specific heat, delta T. It actually calculates the energy transferred over a 30-second time period, all right? So, With this type of a valve, you can then characterize the power curve for a heat exchanger. So for a 24-hour period, if you record that energy, the MC sub P delta T that comes off this valve, you can actually see what the energy curve, the power curve is for a coil, all right? And first time I saw this, I said, that's not what I'm expecting to see. It's significantly nonlinear, but not only that, the energy coming off the coil flatlines and even turns down as the flow is increasing. Okay, at the same time that the energy valve is recording energy and characterizing the energy profile of the coil, it's also measuring and storing the delta T over the as you're increasing flow. If you put these together, you have a situation where you can see the coil delta T deteriorating, but it's deteriorating as the coil has maxed out. And we were, kind of struggling. How do you actually describe that? And we had to come up with some new terminology. So we came up with power saturation point, the point beyond which a coil cannot yield additional heat transfer regardless of increased flow. In other words, you cannot get any more cooling effect into your airstream. Doesn't matter how much more water you're putting through the coil, you're flatlining. If you operate the coil beyond the power saturation point, you're in the waste zone, which is operation beyond the power saturation point. So looking at the coil, we can say that for this particular coil, air handler number 6, we really want to limit the delta T to 12 degrees. There's no point in allowing the flow to exceed a point to which the temperature difference is allowed to go below 12 degrees, because that's the maximum power that you can get out of the coil. The actuator also has a delta T manager controller that resides underneath the existing DDC control. And that actually prevents the valve from opening any further, irrespective of what the DDC control is actually calling for. And what that looks like is this trace right here. This is trending of the gallons per minute as a function of time through the valve. The DDC control signal from both the carrier DDC control and the delta T manager control. Here's the actual delta T that is experiencing across the coil, and then this just tells you when you're actually doing delta T limiting. You're actually overriding the DDC control to prevent the temperature from degrading. So on morning startup, you're about 15, 16 degrees. The chill water coil gets a command to open up. The delta T, as you would expect, deteriorates. The set point is 12 degrees with a -2 degree deadband. In other words, it wants to modulate around 12 degrees, but if in fact the DDC control allows it to go below 10 degrees, then we invoke the delta T limiting controller that resides on the actuator. And that's what happens right at this point. When it goes below 10 degrees, the delta T limiting controller takes over. It recovers the delta T. Once it achieves 12 degrees, it hands control back to the DDC control. Again, the DDC control opens the valve, and sure enough, delta T deteriorates. Once it crosses 10 degrees, again, the delta T limiter control takes over, and it actually hovers around very closely to 12 degrees, and it basically takes over control for the rest of the afternoon. It prevents the DDC control from allowing the coil to go into that waste zone part of operation. Okay, what does that mean from a pumping energy standpoint? If you look at 2 points, Here's 12.5 degrees, 43 GPM. If you operated at 10 degrees, 56 GPM, that's a 24% increase in flow with a 56% increase in pumping energy. But remember what Peter was saying about the real impact, it can be as much as a 4-time multiplier over what your pumping energy is. This actually shows the hours of operation for the coils. The blue data is actual operation when the delta T limiting function is active. And you can see it varies depending on what air handling unit you're actually talking about. Number 6 had a 75% delta T limiting. Number 4 only had a 10% delta T limiting characteristic. Interestingly, at the beginning of the chill water season, that coil was blown out, was replaced with a brand new Heatcraft 14-degree coil. Even controlling to 12 degrees, that 14-degree coil, brand new, was still going to be overflowing to a 10% of the operating time period. Okay, and then for seasonal comparison, in 2010, for the month of August and September, the delta T for the whole building, and MIT has independent flow and delta T measurements for the whole building. So this is not our data, this is MIT data. It had a 6.15 degree delta T. This past cooling season, it had a 12.14 degree delta T. Essentially, we've brought the load delta T up to what the chill water plant is actually looking for. All right, it's especially effective at reducing overflow on power coils that display power saturation, overall reduction in chill water flow. Typically, you can have at least a 25% reduction in flow with in excess of 50% savings on pumping energy. You're maximizing coil performance, you're saving. You can actually document the commissioning of the coil from one season to the next with that 13-month data archive. And that's it.